Imagine a complex software system as a massive empty room filled with floating data. You have integers, text strings, and Boolean values drifting independently. In early procedural programming, this data was kept entirely separate from the functions that modified it. You wrote lines of logic that reached out, grabbed a piece of data, changed it, and put it back. Over time, those lines of interaction crisscrossed, creating a tangled, fragile web of dependencies. As systems scale to millions of lines of code, this separation becomes unmanageable. A function designed to update a user's password might accidentally overwrite a bank balance, simply because the data isn't tethered to anything that protects it. Complexity breeds corruption. To solve this, developers adopted a different paradigm: object-oriented programming, or OOP. Instead of keeping data and actions separate, OOP bundles related data, called state, and the functions that modify it, called behavior, into a single, unified entity. Looking at the core objectives of this framework, we can see exactly how it's structured. We are going to define how blueprints create specific objects, examine how data security is enforced through access specifiers, and distinguish between instance and static methods. Managing modern complexity requires a shift in strategy, moving from the execution of isolated functions toward the design of robust, self-contained objects. The foundation of this design is the class. A class is an immutable blueprint. It doesn't hold actual data itself, rather it dictates the exact structure of what we want to build. The car blueprint defines strict requirements. Any car created must have attributes for a make, model, year, and rental status. When we fill that blueprint with actual information, we get an object. A Toyota Corolla 2020 is a specific instance populated with unique properties. This architecture is highly efficient. A single class definition, like tree, resides in memory once, but it can stamp out hundreds of unique object instances: an oak, a pine, a cherry, each maintaining its own specific height and age. The blueprint also defines behaviors. These are the methods that objects can execute. Because they are objects of the tree class, they all inherently possess the ability to perform actions like growing or shedding leaves. The class provides the structural logic, while the object provides the unique state required for execution. But this raises a mechanical question. When an object is first allocated as an empty block in memory, how does it receive its unique data? The answer lies in the constructor. Looking at this Java class, the constructor is a specialized initialization method that shares the exact same name as the class itself. It triggers automatically at the precise moment a new object is created. Its entire purpose is to catch external data arguments and bind them to the object's internal attributes. We can see this in action during the main class execution. The code calls newPerson, passing in the string Alice and the integer 30. Those specific values travel from the call site through the constructor and lock into the newly allocated memory slots for that specific person object. Without a constructor, an object is just an empty shell. The constructor is the vital bridge between abstract theory and a functional populated instance. Once that object is populated, its data becomes vulnerable. If any external script can directly overwrite an object's variables, state becomes unpredictable, and tracking down bugs becomes nearly impossible. To protect data integrity, object-oriented programming relies on a principle called encapsulation. It strictly secures an object's internal state using access modifiers. By applying the private keyword to attributes, as seen here with the variables name and age, we lock those data points away from the outside world. They are now invisible to the rest of the software. If an external system attempts a direct read or write operation on a private attribute, the compiler throws an error. The request simply bounces off the encapsulation shield. However, a completely isolated object is useless. The rest of the program still needs to interact with this data, but on the object's terms, through controlled public gates. This is why we write getters and setters. These are authorized public methods specifically designed to read and modify the private state. Instead of forcing new data directly into the variable, an external script calls the setName method. The method safely penetrates the shield, validates the input if necessary, and executes the update internally. Encapsulation ensures that an object remains the absolute master of its own state. The rest of the system is forced to play by its rules. Because objects maintain their own unique state, the actions they perform usually require an awareness of that state. You can't withdraw money from a bank without specifying which account balance you're altering. We define these state-dependent behaviors as instance methods. As outlined here, an instance method operates specifically on the data of a unique, initialized object. When an instance method is called, it uses keywords like this in Java or self in Python to explicitly refer to the attributes of the exact object that triggered the action. Because they rely on object data, the syntax requires an initialized object to function. In this example, you must create the obj variable first, and then attach the method called directly to it. Instance methods are inherently tied to state. If the behavior needs to change based on which entity is acting, it must be an instance method. But sometimes a program needs to execute a task that has absolutely nothing to do with a specific object's state, a universally applicable utility. For these scenarios, we use static methods. These are behaviors that belong to the overall class itself, rather than any individual instance. They perform tasks that do not depend on instance-specific data. Since a static method isn't tethered to a specific object, it has no this or self context. It physically cannot access private, instance-level attributes. Notice the syntax difference here. You don't create an object to call a static method. You simply use the class name itself, in this case, example.staticMethod, bypassing object instantiation entirely. This is ideal for operations like running a mathematical calculation or generating a system-wide log entry. Forcing the system to allocate memory for a new object just to add two numbers together would be highly inefficient. Static methods streamline the software, providing global utilities that serve the entire system at a higher structural level. When we assemble these pieces, the architecture of object-oriented programming becomes clear. The class provides the rigid blueprint. The constructor uses that blueprint to stamp out an object, filling it with unique data. That unique data is immediately secured by encapsulation, locked behind private access modifiers, and only reachable through highly controlled public getters and setters. And when it comes time to act, the system intelligently divides the workload. Instance methods handle the state-specific heavy lifting, while static methods provide fast class-level utilities. Data and the logic that modifies it are no longer drifting chaotically in a void. They are tightly bound, strictly governed, and structurally sound. Object-oriented programming establishes a rigorous architecture of containment and control. Designing discrete, self-reliant objects allows developers to organize the massive complexity of modern software into a secure, logical framework.